Hi, we're Group 14. I'm Leah Sanders.
I'm Blair Pellegrin.
Ethan Smith.
And I'm Christopher Eustace.
And our topic is downhole issues affecting electrical submersible pumps, ESPs, in conventional wells. Electrical submersible pump systems are a frequently used example of artificial lift technique and can be used in both onshore and offshore installations. ESPs are put into place after a reservoir has depleted its natural pressure. An ESP provides artificial lift to overcome pressure losses and allow the well to continue to flow. ESPs are very common around the world. In 2000, about 14% of wells in the world were utilizing ESPs. However, ESPs are not approved for wells with high temperature, sand, or gas production. ESPs are also affected by rotational speed, bubble size, fluid density, and viscosity. Pump repairs resulting from these issues can be extremely costly. Controlling these parameters and designing ESP systems with safeguards against these hazards is imperative to creating an economical artificial lift system. The four most common issues affecting the reliability and lifespan of ESPs are viscosity, high temperatures, high gas-liquid ratios, and issues with corrosives and abrasives. For our project, we chose to focus on two main issues for ESPs. These issues can be solved using material science. They are abrasives and corrosives and high temperature. We chose to research these issues because they are the most impactful to ESP failure, and they are largely unresolved in current ESP system designs. We feel that improvement in these areas would be the most beneficial to the profitability of conventional wells.
ESPs are selected by the well and estimated producing fluid temperatures. When the estimates are less than actual temperature, failure is likely. In most cases, the well temperature is less than 200 degrees Fahrenheit, while the fluid temperature can reach above 400 degrees Fahrenheit.
ESPs have thermal ratings. If the thermal ratings are exceeded, motor life is decreased. The rule for this is by every 18 degrees Fahrenheit the system exceeds the thermal rating, the pump life is decreased by half. Because of this, it is very important for lower temperatures to be maintained in the well and near the motor. The main cause of motors overheating is elastomer failure. When ESP's temperatures exceed the design rating, the elastomers used for sealing the ESP from the wellbore contamination can break and melt. If this happens, the fluid entering the system will completely destroy the insulation, destroying the pump.
Heat expansion is the second main cause of ESP motor failure from high temperatures. With the pump system being a very compact device, this can conflict running tolerances. High operating temperatures can create inadequate clearances within the ESP system, causing entry of well fluids and binding and galling of rotating parts.
ESP life is being prolonged through continuous monitoring of ESP systems. Some of these new downhole sensors include motor temperature sensors, well temperature sensors, pump discharge temperature sensors, pump intake pressure sensors, pump discharge pressure sensors, and motor vibration sensors.
Common problems that occur during the first 2 years of ESP operation include abrasion in the gas separator caused by sand production and corrosion in the production tubing due to sulfate-reducing bacteria, CO2, and erosion. Additional problems include sand erosion in gravel packs, corrosion of production casing by SRB and CO2, seal failure, pump failure, electrical problems, inventory, and low run life. There's a phenomena where 95% of ESP failures occur during the first 2 years of ESP life. If failure does not occur within the first 2 years of run life, the ESPs tend to run for up to a decade or longer without failure. This suggests that approximately 95% of ESPs are poorly designed for long-term reliability, and approximately 5% of ESPs are adequately reliable. I think a close study of the 5% of adequately reliable ESPs will make a great starting point for ESP design improvements. We can examine these durable ESPs and aim to design an ESP that will run for the entire life of a well without any issues. This is a plot of the effect of dissolved gas concentration on corrosion. The overall corrosion rate of carbon steel is plotted on the y-axis. Carbon steel is a very common material used in downhole oil field components. 3 different gases are plotted on the x-axis. Each gas has its own x-axis scale. O2 exhibits a linear trend while CO2 and H2S exhibit square root trends. Corrosion mitigation strategies include continuous and batch chemical treatments that may be applied in the wells. Reduction in corrosion rate has a direct correlation to the reduction of workover frequency and will extend the life of ESPs and increase profitability. Chemical injections may be applied downhole through capillary tubing. Corrosion inhibitors, de-emulsifiers, and/or scale inhibitors are injected based on the characteristics of the produced fluids and the operational conditions of the wells. Batch treatments of biocides and surfactants are performed downhole in order to control the SRB activity. This is a plot of mean time between failure improvements over the course of an 8-year period for the South Mona gas unit. The first year consists of a learning period where typical failures include gravel pack problems, high sand production, and corrosion. In the subsequent following year, typical failures include tubing hole, casing hole, and electrical problems in Tucupita and Uracoa. Improvements during this point in time and in the following year include gravel packer with 13% chromium, a change in the ESP design, and improvements in the corrosion mitigation program.
The fundamental question to ask in any well operation is whether or not it's economical. To that end, an ESP is a major cost for any oil company. We had Schlumberger quote us the cost of an ESP for a typical West Texas oil well. Total parts required for the ESP installation are over $250,000. This is a cost that an oil company would be looking at every time they have to replace an ESP, not including the cost for rig time, lost production, rig labor. In this slide, I have summarized the total costs involved in replacing an ESP. With the ESP package starting at $250,000, rig time approaching $750,000, and lost production and rig hands and consumables, the oil companies are looking at cost in a range of $1 million per failure. When we can extend the lifetime of an ESP, this can average down the total cost of the failures and save oil companies a great deal of money in what is currently a very down oil market.
Listed below are our project objectives for spring 2018. We plan to secure a faculty advisor within the Department of Mechanical Engineering and also secure an industry advisor. We plan to research and test materials that can withstand high temperatures and corrosives. We plan to run cost analysis for an ESP system constructed from more durable materials. We want to use CNC and 3D printing software to create a model of an improved ESP design with representation of which parts are made out of which material. And ultimately, we plan to present an improved ESP design idea with improved lifespan that will also improve the profitability of a well. This slide shows the contributions of each group member. And this slide shows the references we used to create this PowerPoint.